Yes. So welcome everyone to the ICTS string seminar. And today we are very happy to have David Tong from University of Cambridge, who will tell us about how to give Chiral Fermions a mass. So over to you, David.
Thanks very much. Thank you for the invitation. You have no idea how much I wish I could be there in person. But my very last trip anywhere was to India to spend New Year in Mumbai and then in Pune with Sunil. That was about 1 billion years ago or something, I think. But it would be nice to return sometime in the future. I'm going to tell you about some work I did with, well, partly based on this paper with Shlomo from last summer. It's a very simple topic. You know, when I discovered the result that I'm about to explain, I was very surprised. I've now been doing this for 6 months, giving these seminars. It seems completely obvious to me that this of course is the situation. And somehow, well, most people I speak to are as surprised by it as I was, but it sort of feels like it should have been known for 40 years or something. It's really a very basic question in quantum field theory that I'm going to share with you. So the question is the following. You get a bunch of fermions, and we all know that massless fermions in quantum field theory have more symmetries than massive fermions. So you get a bunch of fermions, you give the fermions a mass, and you ask what symmetries are broken when the fermions get a mass. That's the only question I want to ask. There's a different story in different dimensions. Everything in this talk is going to be to do with 4-dimensional fermions and continuous symmetries. There's also lots of interesting statements about discrete symmetries, but just the basic 4-dimensional fermions, continuous symmetries. Let me set the scene for you. Here's a simple example. Take a single massless Dirac fermion. It has 2 symmetries, usually called U1A and U1V. U1V rotates both left and right-handed in the same way. U1 axial rotates them in opposite ways. Give the fermions a mass. What happens? Well, the vector symmetry survives, but the axial symmetry or the chiral symmetry, which acts differently on left and right-handed fermions, is obviously broken when you give it a mass. Okay. Quantum field theory 101. A slightly more complicated example, but it's still very well known. Consider QCD, where you have n flavors of Dirac fermions, each of which is massless. So the massless limit of QCD. So this is also an example where the fermions get a mass, the fermions now being the proton and the neutron as opposed to the mesons. You don't explicitly break the chiral symmetry in the Lagrangian. There is a chiral symmetry which acts differently on the n left-handed fermions and the n right-handed fermions. But accompanying confinement and the dynamical generation of a mass is this fermion condensate. And this fermion condensate spontaneously breaks the chiral symmetry. So again, the left-handed and right-handed independent symmetries are broken down to the vector-like subgroup. So you might conclude from this, and I think this is sort of the folklore, that if fermions get a mass, vector-like symmetries can be preserved, but chiral symmetries are necessarily broken. Chiral symmetries being defined as those which act differently on left and right-handed fermions. And the punchline of this talk is that statement isn't quite true. There's a more refined version of that statement about when particular symmetries are broken. All right, so the true statement actually is not a new one. It was known 40 years ago by the work of 't Hooft. So let me remind you what 't Hooft did. So 't Hooft was thinking about anomalies. And when we talk about anomalies in quantum field theory, we mean many, many different things. We should sort of be a bit more careful in our language. The kind of anomalies that were known before 't Hooft were the first 2. So in 4 dimensions, if you can compute an anomaly for a continuous symmetry, it's just a perturbative anomaly. What happens? Well, you could have a gauge current on each 3 legs of the triangle diagram. If you sum over all such triangle diagrams with all the fermions running in a loop and you get a non-vanishing answer, that's bad. If you have a gauge anomaly, your theory is simply mathematically inconsistent. You should just throw it away and start again. That was actually the second kind of anomaly to be discovered, this gauge inconsistency. The first kind of anomaly to be discovered is the axial anomaly or the ABJ anomaly. And in that case, you have 1 global symmetry and 3 gauge, sorry, can't count to 3. 1 global symmetry and 2 gauge currents on the different legs. And again, when you sum over all the fermions in these diagrams, if you get a non-zero answer, what it's telling you is that the classical symmetry of the theory associated to this global current, sorry, my cursor keeps vanishing, associated to this global current, does not survive quantization. So this is, in fact, this is how we usually describe anomalies when we first teach them in a quantum field theory class. We say that an anomaly is a classical symmetry that doesn't survive the quantization of the theory. After work in recent years, I now think that's a very bad description of what an anomaly is. There's something more basic that underlies an anomaly rather than just not surviving quantization. Which brings me to what Hooft did. So Hooft looked at the following diagram. It's sort of the obvious one that's missing. It's where you've got three different global currents on the edge. You sum over all fermions running in these loops. And you see if there's a finite answer, finite meaning non-zero. See if there's a non-zero answer. So what happens? Well, if the Hooft anomaly does not vanish, nothing bad happens at all. The symmetry is still a good symmetry of the quantum system. If it's a non-abelian symmetry, you can all states must fall into multiplets of it. If it's an abelian symmetry, there's conservation laws that come from it. Everything you expect from a symmetry still holds if the Hooft anomaly is non-vanishing. However, the Hooft anomaly gives a number, which is an integer, which characterizes the symmetry. And the power of the Hooft anomaly is that anything you do to the theory, deforming it in any way, letting it flow under RG, this Hooft anomaly number cannot change, provided that the symmetry remains unbroken. So it's a very powerful constraint on the properties of theories which have certain symmetries. And I think a more modern perspective is that the Hooft anomaly allows us to classify quantum field theories. Quantum field theories are first classified, say, by their dimension, and then by the symmetries that they have. And then a finer classification is that each symmetry comes associated with a number, which is the Hooft anomaly for that symmetry. And it doesn't change within the class of quantum field theories that you're studying. All right, let me tell you one of the results that's Hooft's own result from 40 years ago. If you have a theory with a particular symmetry, you calculate the Hooft anomaly for that symmetry, and you get a non-zero answer. Usually we think about these theories in the UV, where things are weakly coupled. You then flow to the infrared. An extraordinarily powerful and simple statement is that if the Hooft anomaly is non-vanishing, you're guaranteed to have massless degrees of freedom in the infrared. And the reason is simple. Either the symmetry is broken or the symmetry is not broken. If the symmetry is broken because it's a continuous symmetry, you must get Goldstone modes. There's massless bosons. If the symmetry is not broken, then this Hooft anomaly can't change under RG flow, which means you have to replicate it somehow in the infrared. But the only thing that replicates these particular kind of Hooft anomalies are massless fermions. So if you have a theory with a symmetry with a Hooft anomaly, you flow to the infrared, the symmetry survives, you're guaranteed that there has to be massless fermions in the problem. You know, a lot of recent work, and actually it was this recent work that spurred my thinking on this. A lot of recent work has considered Hooft anomalies for discrete symmetries. A lot of the story is the same. You can think about the Hooft anomaly as classifying the quantum field theory that has a discrete symmetry, except this statement is not true for discrete symmetries. For discrete symmetries, you can flow to the infrared, and the Hooft anomaly can be saturated by a topological quantum field theory. So you can be gapped, but still have a Hooft anomaly. For continuous symmetries, that's not possible. There have to be massless fermions in the infrared to replicate the Hooft anomaly. All right, so here's an example. This is the example that Hooft actually introduced this for. We go back to QCD, which is SU3 with n massless quarks. And in the UV, the theory has the following symmetry. There's an SUN left times SUN right times U1 baryon or U1 vector. I've not included the U1 axial because the U1 axial suffers the ABJ anomaly and so is not a symmetry of the quantum theory. So you can compute the Hooft anomalies for each of these symmetries. You just put global currents on a triangle diagram and sum over the fermions running in loops. It's basically a group theoretic exercise to compute the Hooft anomaly. And you find that the Hooft anomaly for, there's two that are non-vanishing. There's the Hooft anomaly for just the SUN left cubed, and there's a Toft anomaly for an SUN left squared and a U1 vector. Both of those Toft anomalies, when you evaluate them, are equal to the number of colors. It's not 0. That means that these Toft anomalies have to be replicated in the infrared. So what was Toft's argument? Toft's argument was, suppose 1, the theory confines, and 2, this global chiral symmetry survives. If that's true, there has to be fermions in the infrared that replicate the Toft anomaly, and that means massless fermions. In QCD, the only massless fermions are the baryons, because mesons are bosons, obviously. So there have to be massless protons or massless neutrons in QCD. Of course, it's not what we see in our world, but the question is, could it happen theoretically? So Toft did the following very, very straightforward calculation. It's a little bit of work. I'm not going to replicate it for you, but it goes as follows. You know how the quarks transform under this global symmetry? But quarks combine in triplets to form baryons. And then you can figure out how any possible baryon would transform under this symmetry. And the transformation properties of baryons are different from the transformation properties of quarks, simply because there's 3 quarks in each. And then Toft's calculation is, can you find a collection of massless baryons, massless protons, neutrons, or more exotic multi-quark states, which replicate the Toft anomalies seen by the quarks? And the remarkable answer is no, no such baryons exist. The punchline of which is that if you have confinement, you necessarily spontaneously break this global symmetry G. You have chiral symmetry breaking, and it breaks down to the vector subgroup SUN diagonal of these two, which of course is what we see in the world. So all of this is to say 2 things. One, Toft anomalies are extraordinarily powerful. They tell you that if you have confinement, you necessarily have chiral symmetry breaking in QCD. And in QCD, they also rule out the possibility to have these massless baryons in the infrared. As the talk goes on, we're going to see examples of different theories where you do in fact get massless composite fermions in the infrared. That's going to be important for what I have to say. All right, are there any questions about this? It's hopefully familiar to many of you. It's sort of standard quantum field theory law.
So David, you didn't mention, but in this scenario, you do get massless mesons or light mesons, right? The pions or something.
That's right. So they come, of course, because G is spontaneously broken.
Exactly.
Yeah. So as I said here, that you're guaranteed to get
right.
some massless particles. If the symmetry is broken, they're bosons. If the symmetry is not broken, they're fermions. And so, of course, in QCD we have massless bosons, where massless means 140 million electron volts. It's perhaps not as massless as you might think. Other questions? All right. So what does this mean? It means that there is an obstacle towards giving fermions a mass preserving a symmetry. But the obstacle is not necessarily chirality of the symmetry. The obstacle is the Toft anomaly for the symmetry. So if you have some massless fermions and you want to give them a mass preserving a symmetry, if that symmetry has a Toft anomaly, you simply cannot do it. It's very straightforward, follows from Toft's analysis. However, if you have a bunch of chiral fermions, sorry, let me say that slightly differently. If you have a bunch of massless fermions that transform under a chiral symmetry, meaning left-handed and right-handed fermions transform differently, then if the Toft anomaly for that symmetry vanishes, there should be no obstacle whatsoever towards giving all those fermions a mass while preserving that chiral symmetry G. It's not the case for the first 2 examples I mentioned, but in general, this should be possible. So here is an example. Let's take the standard model gauge group SU3 times SU2 times U1 with 1 generation of quarks and leptons charged under it. Now, famously, the standard model is chiral. The left-handed fermions feel the SU2 weak force. The right-handed do not. Moreover, the representation of the fermions is anomaly-free. And it has to be anomaly-free because in this case, we've chosen to gauge the group G. And so the theory is only consistent if the anomalies vanish. So the question is, is it possible to take one generation of fermions in the standard model and give them a mass without breaking the gauge group of the standard model? Now, the fermions in the standard model do have a mass, but they choose to do it by breaking the gauge group G. There's a Higgs mechanism. They couple 3 Yukawa terms to a Higgs boson. Higgs boson gets a VEV, and of course it breaks SU2 times U1 down to electromagnetism. So the question I want to address is there another way? Is it possible, not necessarily realized by nature, but is it possible in principle to give one generation of fermions a mass without breaking the standard model gauge group, or in general to give fermions a mass without breaking a chiral but anomaly-free symmetry G? That's the question that I want to address in this talk. Any questions about the question? All right. Let me just make a comment. This idea of giving fermions a mass while preserving a symmetry G that you might naively think would be broken because it's chiral has been studied in the context of condensed matter literature quite a lot in the last few years, in particular in the context of SPT phases. In that setup, it often goes by the name of symmetric mass generation. So symmetric mass generation is the idea that it might be possible to give fermions a mass preserving some chiral symmetry in certain contexts. It started really with work of Fitkowski and Kitaev about 10 years ago, thinking about interacting topological insulators and various discrete symmetries. But as I said, here there is a whole story to tell about discrete symmetries. It's in the paper, but here I'll just focus on continuous symmetries. All right, so that's the question I want to ask. How do you give fermions a mass without breaking chiral symmetry? Here's the setup. You have a bunch of massless fermions. And as I said, there's a symmetry G under which left and right-handed fermions transform differently. It's non-anomalous. For the purposes of the discussion, it turns out to be much more useful to think of G as a global symmetry rather than a gauge symmetry. That's obviously a little bit perverse in this case, where G is really the standard model gauge group. Even in that case, I'm going to do this example of the standard model. Even in that case, it's helpful to think of G as a global symmetry, simply because the breaking of global symmetries is a much cleaner statement than the breaking of gauge symmetries. So we can just sort of, there's a whole bunch of other issues that we can forget about if we think about G as a global symmetry. So that's the way I'm going to proceed. All right, so what's the deal? I can only write down interaction terms that preserve the symmetry G. Any mass term, meaning a quadratic term, has a left-handed fermion dagger times a right-handed fermion. If left and right-handed fermions transform differently, any mass term necessarily breaks the symmetry G. That's really what we mean by chiral fermions. So quadratic mass terms are not allowed. Okay, otherwise, it would be trivial. The kind of terms you can write that preserve the symmetry G tend to be multi-fermion terms, 4 fermion terms, 6 fermion terms. Because we're in 4 dimensions, they're irrelevant. The coefficient grows smaller as we flow to the infrared. Such irrelevant couplings can never gap fermions in 4 dimensions, perhaps in 2, but not in 4. So what that means is that given a collection of massless chiral fermions, there's no interaction terms I can write within the fermions themselves that can do the job of giving them a mass. So we're obliged to introduce extra degrees of freedom. So this is the setup, and I'll elaborate on this as we go on. You start with the massless fermions, massless chiral fermions. You introduce some new massive degrees of freedom at a high energy scale that also preserve this symmetry G. And moreover, everything is going to be vector-like under this. They shouldn't change the anomalies of G. What that means is it's totally trivial to give this extra stuff an arbitrarily high mass and just remove it from the story. So what we have to do is take this massive stuff, dial parameters so that it becomes light, allow it to interact with the original massless fermions, and the game is to find a collection of massless stuff which, when it interacts, gives a mass to everything, while preserving the symmetry G. That's the goal that we want. So there's a bunch of caveats that I need for the massive stuff, which I'll now run through. I should say these rules of the game, we didn't entirely make them up. They're very standard in condensed matter literature in topological phases of matter. So what's the deal? Well, we want to introduce massive stuff. Massive stuff can be scalars, fermions, or vectors, and for each of them, there's a little bit of a caveat. So let me show you what they are. Firstly, if the massive stuff is a scalar, there's no problem. Yes, please. Who's talking? I can't see.
Sorry. So
hey,
I just wanted to. Hi, Dave. Yeah. So I just wanted to kind of ask the class of theories that you're thinking about. So when you say that, you're talking about chiral symmetry and so on. So just to make sure that like I'm getting this right. So there's a way of thinking about massless fermions in 4D where you just think of all of them as just left fermions, right? You can just think of all of them as left fermions. And if there's a symmetry group G, they are, let's say, in some representation R of the symmetry group of this thing. So the masses are forbidden if I can say that R tensor R does not have a singlet.
Yes, exactly.
Okay.
Yes.
So that's even without doing any question of anomalies and so on, one can forbid masses that way. So that's a chiral theory, right? I mean
that's a chiral theory, exactly. Then in addition, having specified a chiral theory with that property, you should then calculate the anomaly for the representations R for that group.
Right.
If it's non-zero, there's no way at all you can give these a mass preserving the symmetry. If it's zero, there's a chance you can.
Okay, so do you understand that, right? That this is the context that yes, you have an R, so that R tensor R does not have a singlet.
Yes.
But the anomaly, this coefficient calculated for this representation R is zero.
Yeah, it's a very nice, concise way of saying it, Lothar.
Okay, thanks. Yeah.
Other questions? All right, so let me run you through these caveats.
Sorry, I have a short question, David.
Hi, Tuhin. So, yeah, please.
So when you are thinking of higher, multiple fermions more than 2, are you necessarily thinking of a strongly coupled gauge group as well, which runs it to in the infrared, runs it to even a relevant piece?
Good. There's going to be 2 different symmetries in the game. So at the moment, I've got this symmetry G. This is the symmetry
that's
which determines whether these are chiral.
Yeah.
And I'm going to think of G as a global symmetry.
Okay.
But among the extra degrees of freedom that I'm going to add is some strongly interacting non-abelian gauge theory. Yeah, I will come to that shortly. Yeah, do ask again if it's not clear by the end of this slide. All right, so what are the various requirements of this massive degrees of freedom? You can add scalars. The scalars can transform under G. There's no problem with giving any scalar a mass, preserving G, just mod phi squared will do the job. The trick is that if you've got a scalar that transforms under G, you have to make sure you have enough control to guarantee that it doesn't condense. If it condenses, it spontaneously breaks G, that's game over. That's not allowed. So you have to be careful if there are scalars. Next, among this extra massive stuff, you can add some fermions. And moreover, you can add fermions that themselves are charged under G. However, any fermions in the massive stuff have to come in vector-like pairs where there's a left and a right-handed pair which both transform the same under G. In Logar's language, this massive stuff, if it's all right-handed, should have in R cross R a singlet so that you can give them a mass. It's just needed so that you can make them massive to begin with while preserving G. Finally, as Tuhin already realized, if you really want to drive strong coupling effects in 4 dimensions, and this idea of symmetric mass generation requires strong coupling effects, you need to have some non-abelian gauge dynamics somewhere in the game. Now, I've got a symmetry group G. That should remain a global symmetry group. I'm not allowed to gauge G. Gauging G is somehow removing G from the story. So what that means is that if I want to introduce non-abelian gauge dynamics, and I do, I'm obliged to find another symmetry H somewhere among my fermions, which I can gauge and have some non-abelian gauge fields. So if I do that, there's some requirements on H. Firstly, H should commute with G, and there should be no mixed anomalies between H and G. That's just the statement that when I do gauge H, G remains a good symmetry. Secondly, remember, I've got some massless fermions and I want everything to be massive to begin with. The way you make gauge bosons massive is you Higgs them. So if I introduce some new gauge bosons charged under H, I should have some extra scalars, not charged under G, but charged under H, that just do the job of giving all those gauge bosons a mass. Okay. So this is the setup. Massless chiral fermions plus vector-like heavy matter. And the punchline of the talk is that somehow chiral plus vector can equal vector under certain circumstances. You might think chiral plus vector is always chiral, but as we'll see, chiral plus vector can equal vector. So everything can get a mass when all of these interact, as we'll see through specific examples. In fact, here's the punchline. The goal is the following: find some gauge dynamics of H such that it does what Toft said things couldn't do in QCD. You want some gauge dynamics of H so that H confines without breaking chiral symmetry. The idea being that the chiral symmetry for H is this global symmetry group G, and that if H confined with chiral symmetry breaking, G would be broken, that would be bad. But when H confines without chiral symmetry breaking, I'll show you can always repurpose such theories to give symmetric mass generation for some bunch of fermions. And we'll see some examples. All right, so it's maybe a little abstract at the moment, but the next step is just to give you a couple of examples to see how this works. And there's a question.
Yes, so H is not a subgroup of G. You want H to completely commute with G.
That's right. H and G should be distinct.
It's not like you're. So it's not like you're taking a global symmetry and you're gauging a subgroup.
No, that's losing the global symmetry. It's another reason why I want to think of G as a global symmetry rather than a gauge symmetry, because it's much cleaner to say that G should survive this whole process. Mm-hmm. Yeah. All right, let's do an example. I know that there's a lot of sort of new notation thrown in here, so let's just see this simple example. A bunch of Weyl fermions in 4 dimensions. As Loga said, in 4 dimensions, you can just insist that all fermions have one-handedness. So I'm going to insist that they're all right-handed. So a bunch of right-handed Weyl fermions transforming under a global group G. G is just SUN. And the fermions transform in the following. There's one that's in the symmetric representation. And then there's n+4 that are in the anti-fundamental representation. Okay, it's a well-known collection of Weyl fermions for which the anomaly for G vanishes. In fact, if you've seen this before, it's almost certainly with G being a gauge symmetry, because of course, if the anomaly vanishes, you're allowed to gauge G, and it's an interesting chiral gauge theory. But in this context, I want to think of G as a global symmetry, protecting these fermions and prohibiting me from giving them a mass by just quadratic terms. All right, so what do I want to do? As we saw in the last slide, I want to gauge a different symmetry H. And it's totally obvious what the different symmetry is. There's n+4 of these anti-fundamental fermions, and there's an SUn+4 that rotates them. So what I want to do is gauge this SUn+4. But there's a problem. There's a problem because if I try to gauge that on its own, it's anomalous. So I'm not allowed to gauge it. But there's a way to cancel the anomaly. So what I do is, in addition to these original fermions, I add a new fermion, which is in, this is annoying, I want to say the anti-symmetric. Let me say it's the anti-symmetric bar representation of H. So this new fermion is neutral under G. That means there's no problem giving it a mass preserving G. If I give it a mass, I'm going to break H, but that's okay. But what it does is it means that this fermion, this anti-symmetric bar plus the fundamental bars altogether give it an anomaly-free representation of this group H, which means that I'm allowed to gauge H. In addition, as I said, I have to add new scalar fields. Those new scalar fields are charged only under H, and their goal is that when they condense, they give these gauge bosons and this fermion and these scalars a big mass so that I can just decouple them and leave myself with the massless fermions. Sunil, your camera's on. This means
yeah, because I'm a bit confused. Thank you.
Yeah, good.
So you have these n+4 anti-fundamentals, and you say H is SUn+4, but isn't there an SUn+4 cross SUn+4 chiral symmetry? I'm sorry, maybe I just...
No, everything is Weil here. Nothing's Dirac. So everything is a right-handed fermion.
Sorry. Okay. So they're all Weil fermions. Okay.
All Weil fermions, yeah.
Okay, thanks. So there's a unique, there's a unique H essentially here.
It's a unique H, that's right. Other questions?
So David, just to understand, when you say the scalar that can Higgs H, you want to add enough scalars to Higgs it completely. Like, for example, if I can just add a fundamental of SUn+4, you won't.
N+4 fundamentals of SUn+4 will do the job. Maybe actually N+3 will do the job, but yeah.
Right. Okay. So you want N+4 of them.
Yeah, I think N+3 is fine.
Every
but
one of the.
Either way, it's.
Yeah. Okay. Yeah. Okay. Mm-hmm.
Other questions? All right. So what's the deal? When these scalars condense, everything becomes massive. But now what I do is I just take the potential for those scalars, I tune the mass squared from being negative to being positive. As the mass squared of these scalars become positive, they themselves decouple, but what I'm left with is a strongly interacting gauge theory. The strongly interacting gauge theory is SUn+4 coupled to these fermions. So let me give some names to these fermions and I'll remind you what this gauge theory does. So here's the setup that we have. The first element in the bracket tells you the representation under the G that I care about, this global symmetry group. The second term in the bracket tells you the representation under the new gauge symmetry H. And the two fermions that I started with, I call lambda and psi. And the additional fermion that's charged only under H, I call chi tilde. So this H gauge dynamics becomes strong. What am I left with? Well, I've got a theory which is this gauge group with one object in the anti-symmetric bar and then n objects in the fundamental of H. This is a very well understood chiral gauge theory. It was first studied, I think it was first studied by Georgi actually in 1979 because the early papers refer to a preprint he wrote, but then I've never managed to find that preprint in published form. So I think this was first studied in unpublished work by Georgi, but the first paper on it is by Rabbi Dimopoulos and Susskind. So it's expected to have the following property. The theory is thought to confine, but it's thought to confine without breaking the global symmetry group, which from the perspective of this gauge theory, the global symmetry group is precisely this SUN under which these objects transform. So what does it do? Well, it confines, but the SUN from the perspective of this symmetry group has a Toft anomaly. You know, the full collection of fermions doesn't have a Toft anomaly, but SUN, but the H gauge group only knows about these fundamental ones, and they on their own have a Toft anomaly, which means that if it confines, it has to give rise to a massless composite fermion in the infrared. And these authors, and earlier Georgi, proposed that what happens is you get a 3 fermion bound state, it's a singlet under the gauge group H, and it transforms in the symmetric bar under the global symmetry G. The lovely fact is, as they showed, that this is a good candidate for what happens precisely because it saturates the Toft anomalies in the infrared. So the calculation that Toft showed wasn't possible in QCD, having massless baryons in the infrared, is absolutely possible in this theory, and it's indeed thought that it's what happens. All right, now, however, we're in business. Because if we go to our original theory and we add in the UV, the following 4 fermion term. Now, I said a few slides back, 4 fermion terms are irrelevant in 4 dimensions, But that's only assuming there's no other strong coupling dynamics in play. And in this theory, we know what happens, that the strong coupling dynamics binds 3 of these fermions together to become a single composite object in the infrared, which means that this 4 fermion term is known to be an example of what's called a dangerously irrelevant operator. It's an operator that appears to be irrelevant in the UV, but when you correctly understand the strong coupling dynamics, you find that it gets a very large anomalous dimension, and actually it's a relevant operator in the IR. Moreover, we know what the relevant operator is. It's just a mass term in the infrared. It's a mass term for this composite object coupled with the lambda guy that just sat out all the strong coupling dynamics because it wasn't coupled to the gauge group H. The 4 fermion term preserves both H and G. We've got a mass term. So what's happened here is in the when the dust settles, we've got a gap theory, a theory with no massless states at all, and yet with this global symmetry G unbroken. So it's exactly the kind of example of symmetric mass generation that I set out to find at the beginning. And you can see where the hard work was done, that the hard work was done by the strong coupling dynamics of H, which bound these objects together, and in doing so changed the representation of G into something different. Something that had the same Toft anomalies as the original, but nonetheless was different. And that then allowed this representation here, this fermion here, to bind with lambda. In other words, the strong coupling dynamics took a set of chiral fermions and turned them into a set of vector-like fermions in the infrared.
David,
that's the general trick that we're going to be working with.
One conclusion, this looks very, very similar to the theories that we used to work on, like top color theories, and even in some extensions of extended technicolor pieces, where I mean, this is a variation where right-handed top, for example, is your composite object like your lambda tilde, and lambda in those cases is like elementary fields, right? And where you have some top color group or technicolor group that's confined at a high scale, giving you this. So this is, I think this part is well-known story. No?
You know, that this particular theory has been used in many, many places, and then since I've been giving talks, I've learned about many others. As we'll see on the next slide, it's not technicolor. Technicolor is the idea that, you know, there's some strong coupling effects that gives rise to a condensation.
Yeah, that's what I meant. It's not technicolor, but the technicolor cannot give mass to fermions. That's the reason why top color assisted technicolor or extended technicolor was proposed. Those are like extra umbrellas, right, to produce masses for the fermions in the standard model.
You know, my next slide is on the standard model, so we'll see exactly how we're going to apply this in the context of the standard model. But and you're absolutely right, and you know, I found many papers in the literature. There's a nice one by David Kaplan and Martin Schwartz who tries to use this to solve some flavor problems. And a lot of these ideas have been floating around for many years. But the simple statement that you can use them to give a mass to chiral fermions preserving a symmetry, I've not found anywhere else. And it's an obvious statement, and I'm surprised I've not found it anywhere else. But in some sense, that's all I'm bringing to the table, is that simple statement. Let's go to the next. Do you know, even though I'm sitting in front of a laptop, somehow Zoom has taken over my screen and I can't see a clock anywhere. Can someone tell me the time? How much longer do I have?
I think you're okay. I mean,
yeah.
About 20 minutes.
Okay.
But you can also go a little bit over, David. It's fine.
Okay. I don't like to. We'll see. Okay, so here's example number 2. This is obviously the gauge group.
Sorry, David. Hello.
Hi, Logger. Yeah.
Yeah. Sorry, I had a question about the previous slide before you move to standard model. So in this theory, the second half of the slide, the scalars are not doing anything, right? You don't have the scalars really, right?
That's right. Because they were there just to give a mass to the gauge bosons H to begin with, and then I dial the parameter and the scalars decouple. Yeah, then they've gone for good.
Yeah. So and I'm also worried. I guess, you know, like I have to, you know, calculate and so on. But Adding so many scalars doesn't destroy your confinement and so on. It's not like this theory is like asymptotically free still. And
no, and even if it did, I wouldn't care. And it doesn't in this case. But I don't care because I just give them a mass that's much bigger than the strong coupling scale of H.
Okay. Right. Okay, good. So you start with some place where you have a Higgs, but you're saying that you can just give them masses, sufficient masses, since they're fundamentals. You can just add masses and then
Exactly.
Right.
So the game is somehow within a space of theories defined by the parameters of the theory. You want to find a path within that space where the starting point has the massless fermions, and as you move in the path, you get to a point where everything is gapped, but G remains unbroken along the entire path. That's sort of the picture to have.
Okay, thanks.
All right, let's do the standard model. As Logar already pointed out, you can think of everything as being right-handed in 4 dimensions, and so I've made that choice. The left-handed fermions, I've really taken the conjugate of them so that I should think of them as right-handed. You can see, for example, that the left-handed quarks transform into 3-bar because I've made them right-handed fermions. All right, so this is the representations under SU3 times SU2 times U1 of one generation of the standard model. I've made the phenomenologist slightly unusual choice of choosing the hypercharges to be integer valued rather than 1/6, but it doesn't really change anything. What to say? Again, it's a weird thing to do, but it's simplest if you think about G as a global symmetry, even though it's dumb. If you want to think about G as it really is a gauge symmetry, what I'm going to do is give a mechanism that will give all of these fermions a mass that is arbitrarily higher than the weak scale, say, leaving SU3 times SU2 times U1 unbroken. So that's where we're going with this. All right. What do we do? The first thing to do is to see if there's an extra symmetry group H that I can gauge. And you don't have to stare for long to realize that there's no such H that I can gauge, which means I have to introduce it. So the first thing I'm going to do is, in addition to the standard model fermions, I'm going to add 3 pairs of fermions. These pairs all come in are all vector-like pairs, which means everything in red, I can just write down an explicit mass term and make them as heavy as I like without breaking G. Okay, you can see, for example, that there's a +3 -3 here, there's a 3 and a 3-bar here, a +2 -2. So they're all in conjugate pairs. All right. I've also added some singlets here. You can think of the singlets as right-handed neutrinos if you're a phenomenologist. So why have I done this? Well, you'll see that the first of each pairs coincides with something that was already in the standard model, which means that having added these new vector-like fermions, I do have a symmetry in the game. The symmetry is an SU2 symmetry, which rotates the things in the green boxes, the pairs of fermions in the green boxes. Now I need, well, as I've gauged this, I should also add some scalars, which are going to Higgs the SU2, make everything heavy. If now I just repeated what I did on the previous example, I would uncondense those scalars, give them a big mass, and I would be forced to try to understand the strong coupling dynamics of SU2 gauge theory coupled to 6 doublets. Okay, the number 6 is important here. There's 6 doublets because there's 2 here, and there's 3 here, and there's 1 here. That means that an SU2 gauge theory has an SU6 global symmetry group, and a subgroup of that SU6 is this SU3 times SU2 times U1. Okay. Actually, you can see how it works. It's actually embedded in an SU5 in the same way that the standard model is embedded in an SU5 gut. That the 5 being these 2 and this 3, and this one just standing out. So what's the deal? Well, we have to understand the strong coupling dynamics of SU2 coupled to 6 doublets, but we've got enough understanding of strongly interacting quantum field theories, in particular that this one's been simulated on a lattice, to know that this will break the chiral symmetry. The chiral symmetry in this case being the SU6 the SU6 will be spontaneously broken by a fermion bilinear, and in turn, this the standard model will also be spontaneously broken. So this does not do what we want to do, but we're almost there. The final step is simply to add some further degrees of freedom, which make everything supersymmetric. So what does that mean? It means I add a gaugino, which is in the adjoint of H, but neutral under G. So it's an extra fermion, but not charged under G. And then for each of the fermions in this list, I also add a corresponding scalar field. Like I said, originally I can give all of these a large mass, but what I'm going to do is having started from all this extra stuff with a large mass, tune the parameters until I go to the supersymmetric point, n equals 1 supersymmetry. The nice fact being that now I've got an SU2 gauge theory coupled to 6 doublets, but with n equals 1 supersymmetry. And this is within the class of theories that Nathan Seiberg solved back in the 90s. And Seiberg found many remarkable things of supersymmetric gauge theories in the 1990s. But this particular theory, SU2 coupled to 6 doublets, has the lovely property that it confines without breaking its global symmetry. Again, the global symmetry being SU6, of which this group G is a subgroup. Okay, so we can just look at what the low energy dynamics is. There's an anomaly if the theory confines without breaking the global symmetry, there have to be massless fermions in the infrared. Those massless fermions are meson-like states that are formed out of pairs of any of the 6 objects that are in the green box. So there are 15 meson-like states, 15 because there's an anti-symmetry property. So it's 6 times 5 divided by 2. The 15 massless mesons that come from the strong coupling dynamics of H are just listed on the bottom of the slide. Okay, here's the lovely fact. There are 15 meson states on the bottom of the slide, and there were 15 fermions that didn't play any role in the strong coupling dynamics of H. These are the ones that aren't in the green boxes. You can see that there's 15 because, where's my cursor? 2 plus 6 plus 1 plus 3 plus 3. So the lovely fact is that the quantum numbers of these 15 guys that didn't play any role in the strong coupling dynamics are exactly conjugate to the quantum numbers of the 15 mesons that came from the green boxes. What that means is that, again, I can return to the original theory. I can add a superpotential in the original theory. This just looks like Yukawa terms now. Naively, marginally irrelevant, but as we'll see, actually dangerously irrelevant. These Yukawa terms, each of them pairs up one of the objects outside the green boxes with 2 inside. As you flow to the infrared, the 2 inside bind together to become mesons, and what look like cubic terms in the superpotential actually become quadratic terms in the infrared, and therefore give a mass to all the fermions. The mass happens preserving this G equals SU3 times SU2 times U1 group, because this superpotential preserves this group. So it's an explicit way to give masses to one generation of the standard model, preserving the electroweak symmetry. I should say that for Tuhin and others in the audience, I have no idea if there's any phenomenological interest in this. The only thing I can think of is that maybe you want a 4th generation with mass significantly above the weak scale, perhaps from some cosmological reason. It's hard to do that with a Higgs because you need a very large Yukawa coupling. There is another mechanism to give fermions a mass preserving the standard model gauge group. All right, any questions about this before I change subject?
A clarification, David, if I may ask you. So the if I have understood the framework correctly, what you have in the UV, the particle content as far as G is concerned looks chiral-like, meaning that you cannot form fermion bilinears, which are G invariant. But in the IR, in terms of the so-called composite degrees of freedom, you actually have a vector-like theory.
That's right. That's exactly right.
I mean, that's all there is, right? And you are just, you are matching the theory correctly so that in the IR perspective, it looks like exact vector-like.
That's exactly right.
Yeah. Okay.
But by the way, sorry, somebody else has a comment?
Yes, David, I just had a question just to kind of confirm something that Tuhin said. So this representation does not have a bilinear invariant. That if this is the R that you've written down, R tensor R has no singlet. I'm kind of
For
no,
everything listed here, R tensor R has some singlets which are precisely the pairs in red. So there's nothing to prohibit me giving the pairs in red a mass. Right. That was my starting point. Everything in black cannot get a mass from an R tensor R representation. And everything in black, of course, is the standard model.
Okay, right. So I mean, if you are really taking it seriously, you should add those mass terms and this will combine with these with some like what we do for neutrino mass or something, right?
Yeah. So again, you know, I'm not worried about naturalness arguments here. Given this theory here, I've got a parameter space where I can dial various parameters, masses, vevs, masses, coupling constants, whatever. There's somewhere in that parameter space where everything in red has a large mass, and I've got just the massless standard model fermions. But as I dial that, there's somewhere else where everything becomes gapped, preserving G. That's the way, again, the way to think about it. Does that make sense?
Okay. Right. Okay. But generically, you will have some mixing. You'll have to write a mass matrix and diagonalize it and so on.
Oh, I see what you're saying. If you really want to apply this to for real phenomenological purposes, there's all sorts of extra things, but that's not somehow the intention here.
Okay. Okay, good. And second thing is that, you know, like, of course, supersymmetry allows you to do, you know, like strong coupling dynamics, but is there something you can say without supersymmetrizing?
Yeah, so
with the similar kind.
You know, I quite like this fact that we're using supersymmetry not because I desperately care about, you know, holomorphic objects or care about what's happening at the LHC, but just as a crutch to get some handle on strong coupling dynamics. However, now we know that this works at the supersymmetric point. You can tune yourself away from the supersymmetric point, and it has to continue to work in a neighborhood of the supersymmetric point. So in other words, this phenomenon has to be robust against at least soft breaking of supersymmetry. And the reason is the following, that it's a gapped phase. It's a gapped phase preserving a symmetry G. If you vary the parameters a little bit, gapped phases can't suddenly become gapless because, you know, things happen continuously. So if you were to break G, obviously you'll get Goldstone bosons. But that means that, you know, a gapped phase preserving G, as you vary parameters away from that point, there's a neighborhood for which you retain the phenomenon of symmetric mass generation. So yes, I think that was your question, Logo, right? Susie was useful to get the answer.
Yes.
But it's robust against breaking Susie.
Okay.
There's a comment in the chat from Sergey. Leptons are not electrons and not neutrinos. And then there's a question mark, which I'm happy about because if there was a full stop, it would be wrong. I don't quite understand the question, Sergey. Leptons are electrons and neutrinos. But if you rephrase, I'd be happy to answer. All right. How long do I have?
Sorry, what are leptons, which are not electrons, not neutrinos, what they are?
Sorry, on the left-hand side here, this object in black are the left-handed electrons and neutrinos. But they combine together into a doublet of SU2, which is why they're written as leptons rather than electrons plus neutrinos. And then the stuff in red is the extra stuff that I added. So I'm not quite sure what the question was, but does that answer it?
Yes, so you have about 7 minutes, but I guess you can take a bit more also.
You know, I think I'll take just the 7. Because I can stop this bit at any time, but I'll try and give you some sense of why I was motivated to think about this question. partly from condensed matter perspective, but the condensed matter work has close connections to what I'm going to tell you about. So there is a very old problem in lattice gauge theory, which is how you put chiral fermions on the lattice. And the problem goes back to the theorem of Nielsen and Ninomiya from the early 80s. Although, you know, I gave a colloquium in Cornell last week, and Paul Ginsparg told me that his thesis is basically contains the Nielsen-Ninomiya theorem a year before Nielsen and Ninomiya. He said it never occurred to him to write up a problem. His thesis was trying to solve the Nielsen-Ninomiya theorem, find a way to put chiral fermions on the lattice. He said he didn't think that anybody would be interested in the statement that it's difficult to put chiral fermions on the lattice. Anyway, the Nielsen-Ninomiya theorem tells you that if you try to put just, say, right-handed fermions on the lattice rebels and gives you what are called fermion doublers, or sometimes mirror fermions. I'm not going to go into it, but if you know these things, this picture on the left is a proof of the Nielsen-Ninomiya theorem, where you have left-handed fermions at the origin of the Brillouin zone, and you necessarily get right-handed fermions at the edge of the Brillouin zone. There's another perspective on the Nielsen-Ninomiya theorem, originally introduced by David Kaplan, which is that you think about an extra dimension in space. You make space an interval. Actually, this was a suggestion subsequently by Shamir, but it's basically the same as David's idea. You make space an interval, the extra dimension of space an interval. You put a massive fermion in 5 dimensions, and what you find when you solve the Dirac equation is that you get 2 massless modes. You get a left-handed doubler, so you get a left-handed massless fermion on one edge and a right-handed massless fermion on the other edge. Again, there's a doubling in the number of fermions, but now they're separated in space, an extra spatial dimension, as opposed to being separated in momentum space in the original setup. All right. So the question is then, how do you put a chiral gauge theory on a lattice? The problem is that, actually, let me go back before I do this. The problem is that if you introduce a gauge field, it couples to both the objects at the origin of the Brillouin zone and the object at the end. In other words, it doesn't give you a chiral gauge theory, it gives you a vector-like theory. Similarly here, introducing a gauge field, there's actually some problems which I probably won't get time to describe in 7 minutes, but I could afterwards. There's a problem with making gauge fields couple just to one edge. If you put gauge fields on the lattice, they couple to, necessarily seem to couple to both left and right-handed fermions. So there's an old idea on how to resolve this. The idea goes back to work of Eichten and Preskill in the 1980s. And the suggestion is that maybe one can turn on some strong coupling effects that give masses just to the mirror fermions, just to the fermion doublers. That means in this setup, give masses just to the fermions on the edge of the Brillouin zone. That was actually what Eichten and Preskill were discussing. Or in a domain wall setup, give masses just to the fermions that live on one edge and not the other. Now, there's some issues with this. There's 2 obstacles you have to overcome. The first obstacle is how do you make sure that the interactions are only felt by 1/2 of the fermions, just the fermions at the edge of the Brillouin zone, or just the fermions on one edge. And the second obstacle, which is the one I'll focus on in the last couple of minutes, is how do you design interactions that do what you want to do? Where what you want to do is give a mass to all these fermion doublers, but do it without breaking the gauge symmetry that the object, that the fermions at the origin of the Brillouin zone feel, without breaking the gauge symmetry that these guys feel. In other words, the question of how you put chiral gauge theories on a lattice is really a question of symmetric mass generation. It's exactly what we've been talking about for the last hour. It's how you give collections of fermions a mass, here the doublers, preserving particular symmetries. So Eichten and Preskill had an idea. Eichten and Preskill's idea in this context was to turn on some 4 fermion terms. Actually, they also included some derivatives which helped ensure that just the fermions at the edge of the Brillouin zone experienced the interaction. They turned on some 4 fermion terms, preserving the symmetry G, say the standard model. Actually, they did SU5 gut. and hoped that these 4 fermion terms would give everything a mass. Now, as I've stressed already in this talk, the 4 fermion terms in 4 dimensions are irrelevant, and from a continuum field theory perspective cannot possibly give fermions a mass. But on the lattice, you can rely on what you might view as a lattice artifact. You can take the coefficient in front of this 4 fermion term and crank it up so it's strongly interacting at the lattice scale, at the UV cutoff scale. Now, when you have strong interactions at the UV cutoff, you can achieve things that you can't do in the continuum. And so there was some hope that this might give rise to a phase where the doublers give a mass and the other fermions do not. Sadly, over 25 years, have I got my counting right? 35 years, no one's really succeeded in doing it. Every time somebody's tried to explore this on the lattice, put on these 4 fermion terms, you find that either both fermions get a mass, or the chiral symmetry actually gets broken after all, or whatever you try to do, searching around in this sort of strongly interacting parameter space, you never find the phase that you want, which is where just the doublers get a mass, and these guys do not. I should say there's a caveat to that, which is recent work by Simon Cattrall over the last 2 or 3 months. It's interesting. I think it also has various issues, but yeah, there is a little star against this to no avail statement. All I want to point out here is that the results that we have in the continuum are perfectly designed to achieve this, achieve symmetric mass generation. They don't do it by turning on 4 fermion terms. They don't do it by relying on strong coupling at the lattice cutoff. Everything is weakly coupled at the lattice cutoff. The strong coupling effects happen just when you flow to the infrared, and they're under control because we understand enough about strongly interacting gauge theories to know what happens. So the question, of course, then is, can one use these continuum gapping mechanisms that I've been talking about to try and solve the problem of putting chiral fermions on the lattice? And because I'm out of time, I'm going to skip a few slides and just go to the punchline. The punchline is sort of. The punchline is yes, I believe there is no difficulty at all in taking the ideas that I've described here, discretizing them and putting them on a lattice, where you could, in principle, put them to use in gapping the mirror fermions. The problem is you can show that anytime you succeed in doing that, the theory that you want to simulate is necessarily going to have a sign problem, which means you run into another obstacle. So I've sort of realized I've gone a bit quick here, but I'm increasingly of the opinion that the very famous fermion doubling problem on lattice gauge theory is not really a problem. I think the real underlying problem is a sign problem, which one necessarily has with trying to simulate chiral gauge theories on the lattice. And so I kind of feel that the Nielsen-Minamia theorem is not the obstacle towards simulating chiral gauge theories. The obstacle is the sign problem. All right, I'm going to finish there. Thank you very much for your attention. I'm happy to answer any questions.
Yes, sir. Like, sir, I'm Aziz Lokhandwala from India.
Thanks, David, for the very nice talk.
You're welcome.
Yes, so let me open the floor to questions. So, Aziz,
please.
Yeah.
Yes, sir. Like, sir, it is not, I would say, much related to this. But, sir, like, sir, I have one doubt, actually. Is it somehow true? Like, you have probably seen the recent Nature publication. Like, it was showing up entanglement between wave and particle nature.
So I think the answer is no. I haven't seen a recent Nature publication.
Okay.
What's it on?
Okay, sir. Like, sir, in that article, it was like there was an experimental simulation which was showing that wave and particle states are both entangled with each other. So, like, my question here is, like, sir, does this like neglect the presence of H cut, which was previously to be assumed somehow?
I think I failed to understand what one word, Aziz. Did you say neglect the presence of edge currents or neglect the presence of something else? What?
H cut, sir. Heisenberg
mode.
cut. Heisenberg cut.
Oh, I'm sorry. I think I haven't understood the question, Aziz. It's my bad. Sorry.
No problem, sir.
Tuhin.
I think Loga has raised his hand before me.
Yes, so Loga, please go ahead.
Yeah, hi David. Yeah, sorry. Could you maybe say a bit more about this thing you skipped, if it is about the chiral gauge series in Lattice? I mean, so I see that you have many slides, but so your statement is that is there a general theorem that you guys proved, or what is it? What is the statement exactly?
The statement is twofold. So if I go back to this, there are two issues with this Eichten-Preskel idea. One is, how do you design interactions that gap fermions preserving the symmetry? Okay, so they haven't succeeded on the lattice because they required strong coupling effects at the lattice scale. But now we have many examples of continuum theories that do that. So I think that problem is simply solved. The next problem is, how do you ensure that only the doublers experience these interactions and not the original guys? So that's the problem that remains to be solved. And there's I'll just show you this slide. There's an old idea. Maybe I'll show you this slide. There's an old idea on how you do this with domain wall fermions. It's an idea that goes back to Golterman and company in the 1990s. This is the 5D lattice. I've written down the various lattice sites, and you know, a 5D spinner decomposes into two 4D chiral spinners, and the hopping terms happen as follows between the two 4D chiral spinners. So rather than sort of having one straight 5D interval, it's better to think about it in this zigzag form. One fermion jumps to another fermion. It's just the statement about what the 5D derivative looks like in the fifth direction. So you have these hopping terms. There's a zero mode over here, which is left-handed, and there's a zero mode over here that's right-handed. And the question is, how do you put on interactions that only say this right-handed modes field? So the obvious thing to do is just to try to write down some gauge fields that couple just to the modes on the right of the interval. So this goes by the name of the waveguide approach. It's by Golterman and company. And there's a problem with it. The problem is that you want these guys to transform under a gauge symmetry. But over here, you don't want them to transform under a gauge symmetry because they shouldn't be feeling the interactions. And the difficulty comes when you consider the hopping term at the edge. There's one fermion which has a gauge, transforms under a gauge symmetry, which should interact in a way with one other fermion that does not. And how can you possibly have that interaction? So what they showed was you have to introduce a new field that lives on this link. And then the problem becomes what happens with this field? How does it affect the dynamics? And in particular, does it screw up the chirality here? So in certain simple cases that they actually can show that the worst thing possible happens, that this field decomposes into two, which is one chiral fermion that lives at this edge and one chiral fermion that lives on this edge. So somehow you have left-handed, right-handed, and it's almost like, you know, some confinement thing where you try to kind of break and you get one left-handed, right-handed pair and another right-handed pair. So they did lots of simulations and they argued that this field here can never decouple. So the slides that I've skipped are just a continuum analysis of this same story. And you can show that the field that you have to introduce is actually associated to a Chern-Simons theory in 5 dimensions. And should decouple precisely when the fermions on the edge are anomaly free. But the trouble is, you only see that the fermions on the edge are anomaly free if you do a one loop calculation. But they can't do that on the lattice. They can't do one loop calculations on the lattice because there's a sign problem, and That means that all their simulations that said this approach doesn't work are quenched simulations, but you can also see that this can never work using quenched simulations. It needs you to do these, to include fermion loops. Moreover, you can also see very clearly that there has to be a sign problem if you want to simulate a chiral gauge theory. You know, somehow the essence of a chiral gauge theory is the partition function isn't real. The partition function has an e to the I, very complicated phase, eta invariant for some gauge field background. So you're never going to avoid the sign problem if you try to simulate a chiral gauge theory. And moreover, the attempts that fail precisely because they can't solve a sign problem. So this is unpublished work. I'm not even sure how I'm going to publish it. It sort of feels slightly odd, but as far as I can tell, there's no evidence that this approach doesn't work, even though people ruled it out 25 years ago. It was a bit rambled over, but does that answer your question?
Yeah, so I just wanted to know, is there like a theorem that if you try to do it, you'll always get a sign problem? I mean, or is it like in this model? I mean, what is
there are two theorems. In 4 dimensions, it's simply a statement that the partition function of a chiral gauge theory has a phase that depends on the gauge field. That's the definition of a sign problem. So I think it's clear that you cannot do this in 4 dimensions. In 2 dimensions, there are situations where that phase vanishes. Even though it's a chiral theory, somehow the left and right-handed fermions cancel and contribute equally to that phase. So you do not have a phase. I haven't managed to internalize that theorem yet and understand what it means for chiral gauge theory, 2D chiral gauge theories on the lattice. I can sort of follow the proof of the theorem, but I don't have an intuitive understanding of it enough to see if possibly there's a way around in 2 dimensions. But I think in 4 dimensions, it's just clear. Any attempt to put a chiral gauge theory on a lattice will run into a sign problem.
Okay, just one more question, and then I'll just leave it to others. So this particular continuum theory that you are talking about, is it possible to put that on the lattice and somehow say simulate standard model with 1 generation?
Yeah.
Has anybody looked at it? Or
so there's I gave you 2 examples of continuum theories. One which relied on the known dynamics of a chiral theory to give confinement without chiral symmetry breaking, and the other one which relied on the known dynamics of supersymmetric but non-chiral theories to have confinement without chiral symmetry breaking. The first one you can't put on the lattice because the auxiliary gate, you want to put a chiral theory on the lattice, but the way you gap the mirrors is by introducing a second chiral theory. But then that has doublers, and you just get into this infinite loop. But
maybe the 2 doublers kind of cancel each other.
Sorry, say again.
Maybe the 2 doublers kind of cancel each other.
No, they don't. I did sort of have some optimism along those lines. That's not the way it works. Okay. The supersymmetric theory, there's no problems with putting it on the lattice. The auxiliary theory, this SU2 theory, is vector-like. There's problems with supersymmetry on the lattice, but these are fine-tuning issues. And as I said, you don't have to fine-tune exactly to the SUSY point. You can get somewhere in its vicinity. So I believe there's no problem in discretizing the theory that's needed to put, say, the standard model on the lattice.
Okay, so you think that, for example, this can be used to put 1 generation of fermions in the lattice and without domain wall or
it would be domain wall with this extra SU2 gauge theory just coupled to 1 edge, giving all of these a mass. But there's a sign problem. So I don't see how one can actually simulate using this.
Okay. I mean, but there's just one more thing. I mean, of course, the sign problem is a potential problem. I mean, whether actually in a particular observable we are calculating whether there is a very wild fluctuation in the phase or not is might or might not be relevant. But yeah, but it is a potential problem. Yes. Okay. Yeah, that's all from me.
Okay. Yeah. to him.
Yeah. So so the example that you gave, it is kind of related to that. So if I look at the UV side, where you basically are looking at the electric degrees of freedom of H, right? As opposed to in the IR, when you're looking at magnetic degrees of freedom of H to determine your spectrum, right?
Yeah, I'm not sure magnetic and electric is quite the right language for this, but okay, I know what you're saying. Yeah.
Yeah, or composite operators.
Yeah, exactly.
So,
yeah.
okay, so the thing is that the full spectrum of, I mean, what I meant is in the UV, in terms of the operators, in terms of the elementary degrees of freedom, it's clear to say that the G is completely chiral with respect to G, that degree, right? When you talked about, for example, in example 1, you looked at only one composite operator, which it's lambda tilde, right? That's basically, but there are entire, you know, I mean, there's a complete huge spectrum of operators which I can make H invariant, but non-trivial representations under G as well, right? I mean, did you manage to do the full analysis to say that indeed there is no other degrees of freedom that remains massless, which cannot give mass with respect to others? I mean, that's
so you know, the example 2 is under much better control because we have supersymmetry.
Yeah,
example 1, we're relying a little bit on conjecture. So the Toft anomalies match if this is the only massless degree of freedom. So one would certainly expect that any other H singlet state is gapped and at the order of, you know, lambda QCD or lambda H in this case.
I see.
You know, the other possibility, of course, is that the symmetry is actually broken, in which case you have to find an H singlet scalar which gets a VEV to break it.
So let me correct myself. So when I thought about it, the fundamental difference between what you are doing and what usually, for example, top color assisted Technicolor does, is that when that theory, when the H confines in those cases, they find a composite scalar that has all the quantum numbers of Higgs scalar, right? In the IR, I mean, the IR means 1 TeV scale before electroweak symmetry is breaking, right? That's what I meant.
I see.
But the difference why you cannot take your scheme to use, for example, in standard model is simply because in the IR means that the TeV scale, you know, honest to God, there is only one lambda. There is no lambda tilde.
That's right. So that's why you can't use this for the first 3 generations. That's exactly right.
Yeah.
Yeah, you got to that point quicker than I did. It took me quite a while to realize why this isn't useful to give a little bit of mass to the first 3 generations. It doesn't work that way. Yeah.
Any more questions for David?
Sorry, in your effective theory, you have in Lagrangian the electron term and lepton term. But yes, in effective Lagrangian, in infrared Lagrangian, yes?
This one?
Yes, electron term and lepton term. So electron and lepton, what is lepton if it is not electron?
Let me just see. Are you?
Yes.
Oh, here. Sorry. So if we go back, here. These are the left-handed quarks and leptons, and these are the right-handed ones. So when I say leptons, I mean left-handed guys.
But mass term of right electron, what is it in the mass term of E of yes?
So
yes. What is it?
So the electron couples to the thing I've called E tilde, and E. Oh, sorry, we can read from here. These 2 left-handed leptons pair together to form a meson, and it's these 2 that become what I've called E tilde. So the electron does pair together with two left-handed, but you need two left-handed leptons. So one of them was the guy in red, which obviously is not a standard model field. It's one of my additional fields.
So it is not a mass term.
So this is a mass term down here. It starts off
Mass
as
term what? Right electron, only right?
No, it
not
starts
left?
with the Yukawa term, and then two of those, the scalar and the fermion in the Yukawa term, combine into a new low energy fermion, and that's what I'm writing down in this infrared superpotential.
But your E is right electron, yes, not only right, not
So
left, yeah?
This is right electron, but then the E tilde is a bound state of two UV objects.
Okay, thank you. Thank you.
But by the way, for the phenomenologists, I've discovered that this whole collection of fermions, red and black, is the same as the collection of fermions that people write down in trinification models. The trinification has an SU3 cubed, which isn't manifest here, but the collection of fermions is the same. I don't know the relevance.
Thank you.
Any more questions for David? Yes, so if not, I guess we can thank David again for the very nice talk.
Thank you, everybody.
Thank you, David.
Almost be there. Hopefully, see you in real life sometime.
Yeah, sure. So let me stop there.